For part A, moment of inertia is equal to integral of r squared dm. And since it's a 3D shape, we would have rho is equal to mass over volume. And since there's dm here, we'd want to take the derivative of this and make it isolate for dm. Volume for the shape would just be pi r squared times L. The derivative of that would be 2 pi r L times dr. Now they have both v and dv, you can plug it in for d, for dm. And this could be simplified. We just get 2m r squared dr. Now that we have dm, we can plug it back into the integral. And for the bounds of the integral, it would be from 0 to r. Let's say this is a circle, or the cylinder. This would be at length r. We would take it from the center out. And we can pull this outside of the integral, and we're left with r squared on the inside. And when we take the integral of this, we're left with 1 over 4, r to the 4th. And when we 0 would just make this 0. And when we plug in r here and we multiply by here, we left with I is equal to 1 over 2 r squared. For part B, we're asked to find the angular acceleration. So since the block is pulling the system down, the force would look something like this, minus the tension. Torque is equal to F cross R, which is also equal to I alpha, since both equations are equal to each other. And in this case, the force of the system would be the tension. So TR is equal to I alpha. Isolate for T here, and plug it back into here. So we just get mg minus I alpha over R. Since it's asking us for angular acceleration, we know that linear acceleration is equal to R alpha. So we can substitute R alpha here. Now, if we get both angular alphas on one side, we can factor it out. M1. And then we have and to isolate for alpha, we would just divide this term by this term. So we're just left with this. This gives us 5.44 rads per second squared. And for part C, it asks for linear. But we already have the formula here, so we just multiply this by the radius. This value by the radius. And we are left with 1.63 meters per second squared. So part D is asking for the amount of revolutions after 5 seconds. So theta is equal to omega I t plus 1/2 alpha t squared. It's initially at rest, so this term is just 0. So we just have omega is equal to 1/2 alpha t squared. We're given every value here. So when you plug in all the values, you find that it's 10.82 revs. And part E, we're given a new scenario where a second mass of 2 kg is hung on the opposite of the 3 kg mass. And we're asked to find the angular acceleration. So it's like part B. So the first mass, we know that the mass is pulling it down, so it has to be larger than the tension. And then we can just, since we're looking for angular, we can substitute R alpha here. And then for the second mass, it would be getting pulled by the tension, so it would be T2 minus this would be little r alpha. So the torque acting on the system would just be the tension 1 times the radius minus tension 2 times the radius is equal to I alpha. Now we have to solve for the tension and plug it in. So the tension up here for the first one would just be and the tension for 2 when we plug it in, we would get this. And we would want to get alphas onto one side so we can factor it out. So on the left side, we would just have this. And on this side, we can factor all the alphas out and then take all these terms and divide it to isolate for alpha. So when we do that, we have alpha is equal to, on this side we can factor out G. And then we're left with alpha is equal to 5.08 rad per second squared. For part F, it's same thing. Acceleration is equal to R times alpha. And we know that R is 0.3, so and we would just get like linear acceleration of 1.52 meters per second squared. For part G, it asks for the kinetic energy of the cylinder. So we'd have to find the speed, since it's initially at rest, the amount of potential energy that it gains, we just plug it into KE rots. So omega F since it starts at rest, this would just be 0. And we're given every value here. So we just plug that in to find that omega F squared is equal to 25.4 rads per second. 50. 50.8 rads per second. And the K rots just be 1/2 I omega squared. We have a value here, so we just plug it in and we get the rotational kinetic energy as 34.29 joules. Part H asks for the network after 5 seconds. Since it starts at rest, all the speed that it gains would just be the energy changed. So we have to find the final speed of the system after 5 seconds. So if you find this, seconds, and we have 25.4 rads per second. And we can convert this into linear to find V1 and V2. So we go R omega. So it would be R omega. We get 7.62 meters per second and 0.762 meters per second. And the network just be 1/2 so then we get a network of 523.16 joules.